We've introduced this conflicting set of ideas about the nature of light in the early part of the 20th century between the old electromagnetic theory of Maxwell and the explanation of the photoelectric effect put forth by Einstein in 1905, that we need to view it as photons. And this seems to run into conflict because we know from our experience in optics that to gain an interference pattern or diffraction pattern, we need a wave-like phenomena. So this question was immediately apparent to people in this era, and a very well-known physicist put forth to his student to actually carry out an experiment to see what would happen. So, but again, the idea to remind you is that we have now, what we're saying is that when we talk about Maxwell's theory, the intensity, or the irradiance as we call it, is proportional to E squared, the amplitude of the electric field squared, or the magnetic field, but remember, we can write it in equivalent ways using the relationship between the speed of light, electric field, and magnetic field. But now we're saying that the intensity of the light for fixed, say, frequency, is now proportional to n, the number of these particles, later called photons, arrive at the screen per second, per area. So the question was, well, how can you test these? Like, which one is right? Or does it work? If we know that we do an experiment, you can pull out a laser. You can actually do this with fingers looking at a bright light. Put the fingers really close together, and you'll see interference fringes. You can see it with a light coming through a window with some shades. I do have some images of that. You can do these interference experiments in everyday life. You don't need a laser necessarily. And with a laser, it's much easier, of course. And we know that we see an interference pattern. And we describe that mathematically as a wave. And that satisfies Maxwell's wave equation. So the question is, well, what happens if you do the double slit experiment, essentially, but at very low intensity? And this is what this particular experiment set out to achieve. Now, so in 1909, Rutherford, who was very famous for various things, as we know, put forth this to his Australian student, G.I. Taylor, to carry this out. And we're going to describe it in terms of a double slit. Actually, the experiment he did was in terms of a diffraction pattern, but it's interference nonetheless. So the question is, if you reduce the intensity of the light so much so that you only have a very small number of photons now passing through the device at a time, and again, you want to reduce it so much that you only have one, would you see an interference pattern or not? So the way he did this was to following way. So he had a light-tight box, and he had a gas flame here. So let's make an image of this. So you have a box, and you have a gas source, again, just as described there. That's my gas source. And you see you have a culminating, say, slit to get a beam. And over here you have a double slit. And over here you have a photographic plate that you want to record the image. Now, in order to reduce the intensity of the light, what Taylor did, and we'll describe this, we don't really describe it a whole lot, it's pretty obvious, put smoke glass plates so it gets really dark, and you put those in between. And what this is, this attenuates the light source. So in this way, the light gets very, very dim. And you wait to see what the pattern arises on the photographic plate. Now, in his paper, we'll actually take a look at his actual paper at the end of this, but he said that the light was as feeble as a candle observed from 1 mile. Now, he actually did this with varying intensities of the light to check that everything was working, which we'll see shortly. But again, the idea was that you care about it is it's so dim that really, in effect, if we know the energy of the light, that we should only have one photon going through on average. So this is a crude setup. And again, this distance here, this is about, it's probably less than a meter. Very short range here. And it's a light-tight box. But let's describe this, how this works. Let's put that away. So with the frequencies in light, and again, this is part of the experiments to check what the frequency distribution. Now, it's not monochromatic, but you can take the mean average. Found that with the most attenuation involved, corresponded to about 5 times 10 to the fifth photons passing per second through the slits. So you might think that's a lot. That's 500,000 photons passing through per second. That sounds like a lot. However, if you take an average and figure out what the spatial separation of each photon is, you take that number, or you take the speed of the particles and divide it by how many are passing per second. This gives the average distance between them. So all you need to do is take the speed of light, 3 times 10 to the 8th meters per second, divided by the rate at which they're coming, and that gives you the average distance that the photons are traveling. Now, this particular analysis here, this assumption here, if you will, that you're getting the spatial separation so large, is, I say a little naive, but it was later known that light has particular properties that actually, this is not actually a foolproof single photon measurement. And it took, again, I'll say it now, we'll come back to it later, it took until 1982 to actually experimentally verify that you do have a single photon state, and then you observe the results of this particular experiment as well. So it's consistent with what we see, but like many of our experiments, like the bending of light around the sun, we know that there are issues that came up that, okay, well, we need to adjust. But this is actually does work. This is actually the result we care for. Now, and again, we'll talk about the true nature of light in the next lecture of what we're sweeping under the rug at this point. Now, what he did, so he set this up. Oh, and also remember that the distance between them was 600 meters, and we said the box was about maybe a meter or so long. So this gives you great confidence, modulo that my statement just prior, that only one photon is passing through the slit at a time. So what did he do? Well, he set it up and he put the box away, and for the most attenuation, the highest attenuation, he put it away, exposed it for 3 months. That's how dim it was to get an image. And the question is, what did he see? Well, as you probably can figure out, and you probably knew already, he observed an interference pattern. And again, here's the caveat again. We'll come back to the true nature, but again, this is there's nothing incorrect in this result. It's just that it may not actually have been, probably was not, single photons that were sending through, because they do tend to bunch for ordinary light sources, and it takes a lot of effort, extreme effort, I would say, that was not available at 1909 to actually come up with single photon states. Okay, so let's just make a crude animation of what's going on here. Now again, in the real experiment, it was a diffraction experiment, but here we're just going to discuss it in terms of the double slit. Now in this case, we have our single photon source, again coming from the attenuated light source, impinging on the double slit, and we want to see what happens on the screen. In what follows, I might have to draw on the screen, but let's take a look. Essentially what happened, again, well, we'll cover this in a minute. Okay, so let's take a look here. So now this is essentially what he's, if you will, it's just an animation of the process. This is our photographic plate, if you will, and the strikes are coming one at a time. Now, there was another feature here is that when you look with a microscope at a photographic plate, what it's really made up of is silver halide grains, and they're about a micrometer across, 10 to the minus 6 meters. Now, and you can see with a microscope that the individual grains are being exposed. Further evidence that you're getting single photon strikes because you're exposing single grains of silver halide. But we see here that over time, as we send in each photon, we get this interference pattern builds up over time. Okay, so again, what we have a single photon strike here, and over time, as we say, builds up the interference pattern, which will show the pattern here, just mathematically, the intensity being plotted, say, this way. That's the intensity as a function of x, say. Now again, this idea is, for photons, we have this caveat, of course, And Taylor carried it out, and he did observe these interference patterns. And this is quite shocking. I mean, this is really the essence of the mystery of quantum mechanics, as Feynman said, is that we're talking about single photons. We start off with single photons, perhaps, but we'll assume we do. Now, if it's a localized particle throughout, it goes through one slit or the other, and we know the pattern depends upon the distance between the slits. So somehow this localized particle needs to know about the location of both slits, and that's even assuming it is a localized particle before we measure it. And we will discuss that again, and we'll repeat this again. Now, this particular experiment, with photons, you can do. It turns out nowadays we can do it with electrons in a much easier way because electrons are much easier to control and much easier to verify that you have a single electron. So these experiments are quite common now, though not every day, but you can carry out these single quantum objects. They form an interference pattern. So if you send electrons through an appropriate double slit, you will see an interference pattern. And we'll return to that, the significance of that, when we build our model, quantum mechanics, in the next few lectures. All right. Lastly, let's just look at the paper. This is kind of an interesting, just historical fact. In the Proceeding of the Cambridge Philosophy Society, it's 1 page long. And this is really kind of unusual in physics, especially nowadays when we have, if you look at recent results of LIGO and stuff, the author list is actually 4 pages, 5 pages long. However, it goes through and he gives a summary of this experiment. And here he talks about the smoke glass screens that were used, talks about checking everything, making sure that the intensity right, how to get the exposure right, but also to determine the energy, which is over here. And again, down here it says the longest time was 2,000 hours, or about 3 months. And again, they says no diminution in the sharpness of the image, so the interference pattern, if you will. And this is how to determine that. So here are the numbers again, 5 times 10 minutes ergs per second. So again, it's in ergs, but again, it's telling us how we do that. But again, just for historical reasons, this is the actual paper.